Now we have this technical session with Dr. Darren Broom. Of gravimetric equipment, most of us do know, and now it's coming with this news, measuring binary gas adsorption equilibria. So I think, Darren, we are all eager to learn a little more about it. I've seen that a paper has just been published in IECR. So without further ado, the word is yours.
Thank you. Right, if I just share the screen now. Is that okay? Is that visible now?
Yes, just fine. We see and hear you.
Great. So good afternoon, everyone. My name's Darren Broom. I work for Hiden Isochema in the UK. We're a manufacturer of gas and vapor adsorption instruments. And I'm going to talk to you about measuring binary gas adsorption equilibria using a new technique we've developed called the integral mass balance, or IMB method. So most of the content of this talk is based on the paper published very recently in Industrial and Engineering Chemistry Research. The reference is over on the right-hand side. I'll begin the talk with an introduction. I'll then move on to the method itself, and then I'll show you some binary nitrogen and oxygen adsorption measurements that we've used to validate the method. I'll show you some isotherms and then the calculated selectivities, and then conclude with a summary. So measuring multi-component gas adsorption equilibrium isotherms is required for most practical gas adsorption applications. We've seen already this week that separations always involve more than one gas. The only exception really is storage applications. Multi-component gas adsorption measurements are needed in order to design and optimize gas separation processes that involve adsorption. We can use models such as the ideal adsorbed solution theory to calculate multi-component adsorption from single component data. And these models are very useful, but the calculations must always be checked using experiments. Now, one of the key points is that existing techniques for making these measurements can be rather time-consuming. With the most accurate techniques, data collection can be as slow as just a single data point per day. So as a result, we recently introduced a new approach, which we call the integral mass balance, or IMB method. Now, with regard to existing techniques, there are two main types of apparatus that are currently used to measure multi-component equilibrium. We have closed systems in which we circulate a gas mixture through an adsorption column, and then also open flow-through systems that are used to measure breakthrough curves. There are other variants on these techniques. You can combine the volumetric and gravimetric method, for example, and that's just another type of closed system. There's also the total desorption method, in which an open flow-through system is used. Following equilibrium, you seal the system off and desorb the contents of the bed into a separate volume for analysis. Those methods measure total amounts adsorbed, but there are also techniques where you can just measure differential adsorbed quantities, so delta N rather than the actual N. Examples include concentration pulse chromatography and also isotope exchange. Now, these various methods have both advantages and disadvantages, but the most accurate methods, which tend to be closed systems or the total desorption methods, are very slow. Before moving on to the IMB method itself, I'd like to focus on the open volumetric system. So we have a schematic over on the right-hand side here showing the adsorption column. In this technique, we control the inlet molar flow rate and the inlet molar composition, and then we measure the outlet molar flow rate and outlet molar composition. We do that as a function of time, and then you can actually integrate that to calculate the amount of gas adsorbed using an expression like this one on the right-hand side. There's a gas phase accumulation term that's subtracted from the integral. Now these methods are relatively quick, or this method is relatively quick, but the accuracy of the measurement in terms of multi-component measurements depends crucially on the accuracy of measuring the outlet molar flow rate. You're measuring the flow rate of a gas of changing composition, and any error in that will accumulate through the integration. So the integral mass balance method that we've now developed combines an open system with in situ gravimetric measurement. So we control the inlet flow rate and the inlet composition, and then we determine the outlet composition using a quadrupole mass spectrometer. At the same time, we measure the sample weight change as a function of time, dW by dt, using a microbalance. This allows us to eliminate the need to measure the total outlet flow rate. We can have fast equilibration times using this technique because we've got an open system. We can control all of the gas properties, the total pressure, the temperature, and the gas phase composition, but we also have higher accuracy. In addition, we can measure multi-point isotherms automatically using this setup. So we have another schematic, but this time of the IMB method reactor over on the right-hand side. Here we've converted the inlet flows and inlet composition to mass quantities rather than molar quantities. If we look at the total mass balance, we can see that actually the total outlet flow rate, F out, can be expressed in terms of the inlet flow rate and the change in mass as a function of time. So we can then substitute in the F in minus dm by dt term to the integral for an open system. That's the same expression, just for clarity. And we can then split that integral into two separate integrals, a flow term and a mass term. One of the interesting things about this is that both integrals in that expression vanish under steady state conditions, and that's because the inlet composition must equal the outlet composition under equilibrium, but also dm, the change in mass, will tend to zero. Now that expression I've just given you there is delta M, and that's just the change in the mass of each component in the IMB reactor. To calculate the actual amount of the component I adsorbed, which we've termed delta N I adds, we need a couple of corrections. The first is the gas phase accumulation term, similar to the open volumetric system. And the second is the corrections for buoyancy, because this is a gravimetric measurement. So in fact, the final equation for this method has 4 terms on the right-hand side. So rather than just the previous 2 terms, we have 2 additional terms. So we now have 1 integral for flow, 1 integral for weight, that's the weight measured by the microbalance. Then we have an integral that accounts for the buoyancy, and then finally a subtracted gas phase accumulation term. Now it's important to note that this is general regardless of the number of components. So I'm focusing on binary mixtures in this talk, but in principle this should apply to ternary or higher mixtures as well. So we've implemented this in an intelligent gravimetric analyzer shown over on the right-hand side. The sample is suspended from a beam balance in the main cabinet. And we control the gas composition using a bank of mass flow controllers, or MFCs. The total pressure in the system can be regulated by a stepper motor controlled valve that's situated on the outlet of the system. And then we analyze the composition using what we call a dynamic sampling mass spectrometer. We've designed a special reactor to implement this technique. The gas mixture enters the base of the reactor via a gas diffuser at the base of the column here. We have a sample suspended in a stainless steel mesh holder. Can hold about 3.5 grams of sample. And then once it's passed through the column, the gas mixture passes through a narrow chimney, above the sample. The mass spectrometer is then connected at this place here via a capillary to that monitors the pressure drop from the measurement pressure down to the vacuum required in the mass spectrometer chamber. So to validate the technique, we've chosen to make binary nitrogen and oxygen adsorption measurements on a commercial 5A zeolite. We chose this because Orhan Talu, who we're working with on this, published data on this sample back in 1996, and he still had some of the sample available. The study included measurements made on an open volumetric system at Cleveland State University, but also measurements made on a closed volumetric system at Air Products Inc. in Allentown in the US. Column size is 70 millimeters by 13 millimeters diameter, and we used about 3.5 grams of sample. We activated the sample under a helium flow at 300 degrees centigrade, and the total pressure was 9.15 bar to match the original study. The crucial point here really is that the total measurement time for a 20-point binary isotherm was only 4 hours. So this is the final data in terms of the binary adsorption isotherms. We have the open symbols showing the original Talu et al. Data, and then the closed symbols are the data using the IMB method. There's some scatter in the original data, but in general we see good agreement. This was quite satisfying. Because this is an automatic measurement that's fairly quick, we were able to run repeats. So we did 9 repeats, so 10 data sets in total to show repeatability. You can see that there was very good agreement between each data set. So this is a plot of 200 data points, 10 repeats over the same conditions. Moving on then to the selectivities. I didn't mention before that actually the 10 runs were run in both directions, from oxygen to nitrogen and nitrogen to oxygen, to check that that there wasn't an effect in terms of the flow patterns between the different directions. But the selectivities that we calculated are shown by the cluster of points here. The open symbols show the original Talu et al. Data. The dashed lines are the upper and lower uncertainty bounds from the original Talu et al. Study. And then the dark line, solid line, is IAST calculations made in the original work. And you can see there's good general agreement. We're basically between the experimental results published before and the IAST predictions. And then finally, we have the average selectivities from all 10 runs, shown here with 2 different types of calculated uncertainties, where the uncertainties increase at either end of the composition range, as you would expect. And with that, I'll summarize. So existing multi-component gas adsorption measurement methods tend to be either time-consuming or inaccurate. So we've developed a new approach, which is called the integral mass balance, or IMB method. And this combines an open volumetric system with in situ gravimetric measurement using a microbalance. This has allowed us to measure binary gas adsorption isotherms in a matter of only hours. And we've used existing oxygen and nitrogen binary gas adsorption data on a 5A zeolite to validate the method. I realized I didn't have time to discuss its full range of applicability, but I'll just note that further work is certainly required to determine over what range of pressures and gas mixtures and so forth the technique will actually work as well. And with that, I'll conclude by thanking you for your attention and mentioning that Hiden Isochema is represented in Brazil by Lab Solutions, and Eduardo from Lab Solutions is present here, and I'm sure he'll be happy to discuss with you in Portuguese if that's easier. Thank you.
Thank you very much, Darren, for such an interesting talk and the possibility of having an instrument that combines dosing of the gas phase with a mass spec and also a gravimetric design, gravimetric devices is quite appealing to all of us. I do not have questions, specific questions so far in the chat, but I would take the time to ask for you to comment about the degree of mixing of the gases. Maybe I lost something, but I don't remember how the gases or the different gases that you dose flow into the chamber. Some of us have been trying to do this kind of measurement with simple manometric devices where you load a given amount of gas 1 and then a given amount of gas 2 by using equations of state. And one of the tricky things is that you should use pumps and things to ensure that the gas phase is homogeneously mixed. So could you comment on that about this device from Hiden? How do you make sure the mixture is homogeneous?
Yeah, that's a very good point. We introduce the mixture into the column via a GC switching valve. So we prepare the mixture. We're flowing from MFCs, and they just join in a sort of fairly standard T. But we're making the assumption that they are mixed, and also that the gas diffuser, which is really just a mesh or similar, just at the base of the column, is sort of mixing the gases sufficiently. Of course, we're also constantly monitoring the gas mixture composition on the outlet. So we do actually, one of the starting points was to make blank runs. So you're measuring the gas composition with just ballast in the holder, just beads or something like that. So if there was some problem with the gases not mixing, I think we'd see that quite clearly from the mass spectrometer signal in blank runs. But it's really it's the flowing nature, I think, that makes the difference. If you put a single gas into a static volume and then try and flow a second gas in without a lot of mixing, pumping and circulation, you're relying on molecular diffusion from one gas to the other, and it's not very effective, I don't think.
Okay.
A very good point.
I will stretch a little bit to allow for some questions that are coming in. Well, Arvind is also asking some questions, and both Leonardo and Deborah, who are Brazilian postdoc fellows who got to know you, are sending their regards. Leo is asking whether this is applied for H2S and if it measures the absolute isotherm. And I'll go straight to the comments of David, Danachi, and Arvind. And you may answer very briefly each one of them or leave for further talk later on. Danachi is asking, have you attempted mixtures of strong and weak adsorbates? For example, 70% hydrogen and 30% CO2. Would the change in H2 composition be difficult to measure, for example? And Arvind asks, one of the challenges in closed loop systems is the need to add additional mass of adsorbent to significantly change the gas phase composition in order to overcome the sensitivity of the second measurement. Does this system overcome this limitation? Many questions, you can choose which to pick.
Yeah, so in a way, the H2S question and the other mixtures, the H2 and CO2, are similar in a way. We've only measured a small number of gas pairs so far. H2S is too corrosive to the microbalance that we're using in this instrument. So in this particular setup, we would not be able to make that measurement. But we do have another instrument that's called the ZEMIS, which can work with corrosive species. but we're still in the process of looking at implementing the IMB method with that type of microbalance. With regard to the hydrogen and the carbon dioxide, a key potential error source from this method is the buoyancy correction that relies on knowledge of the density of the mixture. There's uncertainty when switching from one composition to the next that increases when the differences in the molar masses increase. So with a light gas and a heavy gas, there is likely to be more uncertainty. We think that should be okay, but we still need to test it.
I will have to wrap up. I'm sorry.
Yeah.
We have sessions starting now in 10 minutes time. Sorry, Arvid, I guess you can then check with Darren about your question. We will move on then. I would just like the chance that I have the word to invite you all at 5:15 p.m. The last session is going to be the General Assembly of the newly found Brazilian Adsorption Society. So everyone that's registered is welcome to come, even though I think we will speak more Portuguese than English. But anyway, just to remind you about that. Thank you, Darren, so much for this interesting presentation and application. And see you around in the sessions. Bye-bye.
Thank you.